In the fall of 1947, in military surplus yards across America, one of the most powerful engines on Earth was being sold for pennies. They sat in the dirt, massive supercharged V12s weighing nearly 3,000 pounds and displacing 2,500 cubic inches. Just a few years earlier, three of these Packard 4M2500 engines were strapped into every wooden PT boat in the South Pacific, generating up to 1,500 horsepower each to hunt enemy warships in the dark. Now, Midwestern tractor pullers and civilian hydroplane racers were dragging them home to build homegrown mechanical monsters. The engine had won a war, but it could not survive peace. The Packard Marine V12 was an aircraft design forced into the ocean, and it demanded thousands of gallons of highly explosive 100-octane aviation fuel. On a wooden boat, that fuel turned the engine room into a floating time bomb. Once the fighting stopped, the United States Navy realized they could never run a gasoline sea monster again. But the real story of the Packard 4M2500 is not only the story of surplus Detroit iron sold for scrap. It is the story of how America built the most dangerous marine engine in history, and why the military, the market, and the future of fuel had to leave it behind. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific engineering problem inside a Detroit laboratory in 1939. In the late 1930s, the United States Navy recognized a terrifying gap in its coastal defense and offensive capabilities. The threat of another global war was rising, and naval planners understood that they could not rely entirely on massive, slow-moving battleships and destroyers. They needed a Mosquito fleet, a swarm of fast, agile, shallow-draft torpedo boats that could hide in coastal waters, sprint out into the open ocean, launch a devastating attack on larger enemy warships, and outrun the return fire. The boats would be made of mahogany and plywood to keep them light. But the real problem was not the hull. The problem was the power. Before 1939, America simply did not possess a marine engine capable of doing what the Navy required. To make a heavily armed 80-foot wooden boat plane across the water at 40 knots, the military needed an engine that produced massive horsepower but weighed almost nothing. The American industrial landscape had no immediate answer. At the time, the diesel engine, an engine that ignites fuel by compressing air until it becomes hot enough to burn diesel fuel, was the standard for heavy marine work. In a coastal tugboat or a commercial fishing vessel, a diesel block provided unmatched durability and low-end pulling power. But those engines were cast-iron behemoths. Putting a standard marine diesel into a lightweight torpedo boat would sink it to the waterline and ruin its speed. On the other end of the spectrum, standard automotive gasoline engines were lightweight, but they were hopelessly underpowered for naval combat. The military needed a miracle of power-to-weight engineering. They found it not in a shipyard, but in Detroit, Michigan, at the Packard Motor Car Company. Packard was primarily known for building luxury automobiles, but the company possessed a deep, institutional memory of high-performance aviation power. During the First World War, Packard engineers had helped design the famous Liberty L-12 aircraft engine. As the 1930s drew to a close, the Navy approached Packard with an impossible request: take the DNA of a high-altitude aircraft engine and force it to survive in the ocean. This process required extreme marinization. Marinization is the engineering process of adapting an engine designed for dry land or the sky to survive the corrosive, water-soaked, heavy-load environment of a boat. The physics of the ocean are entirely different from the physics of the sky. When an aircraft engine reaches cruising altitude, the air is clean, cold, and dry. The propeller encounters relatively low resistance, allowing the engine to settle into a steady, comfortable rhythm. The engine cools itself efficiently as high-speed freezing air rushes over the metal. The ocean offers none of those comforts. Water is nearly 800 times denser than air. Pushing a heavy wooden boat through the water requires an engine to fight a constant, relentless wall of drag. An aircraft engine in a boat does not get to coast. It is perpetually running uphill under maximum strain while inhaling a destructive mist of corrosive saltwater. To solve this, Packard engineers in Detroit dug into their archives and began heavily modifying an older V-12 aircraft design. A V-12 is an engine with 12 cylinders arranged in two banks angled in a V shape, a layout that naturally balances the violent internal forces and allows for massive power delivery. The resulting prototype was a mechanical Leviathan. The engine displaced 2,500 cubic inches. Displacement, the total volume swept by the pistons inside the cylinders, is the foundational metric of an engine's breathing capacity. For context, a standard American passenger car, V8 in the 1950s, might displace 300 cubic inches. The Packard Marine engine was more than 8 times that size. To keep the weight from destroying the boats, Packard could not use traditional cast iron. The massive block, the main engine structure that holds the cylinders and major internal parts, was cast entirely from aluminum alloy. Aluminum was expensive, difficult to cast at that scale, and considered a precious wartime material, but it was the only way to keep the engine's weight down to roughly 2,900 pounds. By late 1939 and early 1940, the first prototypes were roaring on dynamometers inside the Detroit factory, but making the engine spin was only half the battle. The heat generated by displacing 2,500 cubic inches of highly combustible fuel under continuous marine load was enough to melt the aluminum internals. Packard had to design a complex dual-loop cooling system. It used a fresh water loop circulating inside the engine block to regulate temperature, which was then cooled by raw seawater pumped in from outside the hull through a heat exchanger. To extract the power the Navy demanded, natural aspiration was not enough. The engineers fitted the engine with a massive supercharger. A supercharger is a mechanically driven air compressor that forces more air into the engine, allowing it to burn more fuel and generate massive power spikes. Driven by a gear train directly off the engine's crankshaft, the rotating shaft that turns piston motion into rotational power, the supercharger screamed as the RPMs climbed, shoving a highly pressurized mixture of air and high-octane aviation gasoline into the 12 cylinders. When the first engines were delivered to the Elko Naval Division in Bayonne, New Jersey, and Higgins Industries in New Orleans, the boat builders realized they could not just use one. To meet the Navy's speed requirements, they strapped 3 of the massive Packard V12s side by side into the plywood belly of each PT boat. The early reception was a mix of awe and terror. The initial versions produced 200 horsepower each, giving a single 80-foot wooden boat an astonishing 3,600 horsepower. Mechanics and test pilots operating the first hulls out of New Jersey quickly learned that the Packard 4M2500 was unlike any marine engine ever built. It idled with a heavy, menacing mechanical clatter, but when the throttles were pushed forward, the supercharger spooled up with a deafening high-pitched scream that echoed across the bays. Packard had a working prototype and a massive military contract, but building one functioning engine in a Detroit laboratory was a completely different problem from building thousands of them on a high-speed assembly line and keeping them alive in the hands of teenage sailors in the humid, desperate waters of the South Pacific. When the Packard 4M2500 V12 moved from prototype testing to full-scale production in Detroit, it ceased to be just an engineering experiment. It became a localized industrial empire. The Packard assembly lines, previously dedicated to building smooth, quiet luxury automobiles, were radically reconfigured to cast, machine, and assemble massive aluminum engine blocks at an unprecedented scale. But the true breakthrough of this engine did not happen inside the factory. It happened when boat builders at the Elko Naval Division in Bayonne, New Jersey, and Higgins Industries in New Orleans had to figure out how to put this immense power into the water. One engine was simply not enough to meet the United States Navy's speed requirements. To push a fully loaded, heavily armed 80-foot mahogany and plywood hull to 40 knots, the boat builders installed 3 Packard V12s side by side in a cramped, poorly ventilated engine room. This configuration created an immediate mechanical crisis. When an engine turns a propeller, it generates torque, twisting force, often felt as the pulling strength of a machine. If 3 2,500 cubic inch V12s all spun their crankshafts in the same direction, the combined torque would physically twist the lightweight wooden boat in the water, making it nearly impossible to steer. To solve this, Packard engineers had to build the engines to counter-rotate. The port and center engines rotated in one direction, while the starboard engine was built with a reversed firing order and a reversed camshaft, the shaft that controls valve opening and closing, to spin in the opposite direction. This canceled out the twisting forces, allowing the wooden hull to track straight across the ocean surface. Keeping three massive engines synchronized required a complex fuel and breathing system. The heart of the Packard 4M2500's power was its forced induction. Each engine was equipped with a centrifugal supercharger, a mechanically driven device that forces more air into the engine by spinning an impeller at thousands of revolutions per minute. As a boat captain pushed the throttles forward, the supercharger spooled up with a distinct, high-pitched scream, ramming highly pressurized air into the intake manifolds. To mix with that pressurized air, the engine required a carburetor, a device that mixes fuel and air before the mixture enters the cylinders. Packard utilized massive Holley downdraft carburetors, originally designed for high-altitude aircraft, mounted high on top of the engine block. These carburetors did not feed standard motor oil or heavy marine diesel fuel. They required 100-octane aviation gasoline. In the 1940s, 100-octane fuel was a triumph of American refining, formulated specifically to resist premature detonation under the extreme cylinder pressures of supercharged aircraft engines. It was incredibly volatile, evaporating quickly and igniting with violent, explosive force. At wide-open throttle, the three Packard V12s consumed fuel at a staggering rate of nearly 300 gallons an hour. To feed them, an Elco PT boat carried up to 3,000 gallons of high-octane aviation fuel in massive tanks housed just below the plywood deck. The boat was essentially a floating gas station wrapped in wood, powered by three open exhaust aircraft engines generating sparks and extreme heat. The physical environment of the boat was the exact opposite of the sky. To prevent the engines from melting themselves under continuous marine load, Packard perfected the heat exchanger, a cooling device where the hot, fresh water circulating inside the engine block is cooled by cold, raw ocean water without the two fluids ever touching. Seawater was scooped up from beneath the hull, pumped through the exchanger to draw heat away from the engine, and then dumped back into the ocean along with the exhaust gases. This precise mechanical arrangement created an entirely new American service network, one built not in roadside garages or traditional shipyards, but in forward operating bases on remote islands in the South Pacific. The Navy had to train a massive workforce of young mechanics, many of whom had grown up repairing simple, low-compression tractor engines on Midwestern farms. Suddenly, they were standing in the humid, suffocating, 100-degree engine room of a PT boat anchored off Tulagi or New Guinea, trying to synchronize the valve lash and fuel mixtures of three supercharged, 4-valve per cylinder aviation engines. Maintenance in this environment was relentless. Spark plugs fouled constantly because the engines were frequently idled during slow-speed night patrols, a condition the high-strung aviation design absolutely hated. The V12s were engineered to run hard, fast, and hot. When forced to creep through the dark to avoid enemy detection, the massive Holley carburetors would load up with unburned fuel, and the mechanics would have to pull, clean, and gap 36 spark plugs the very next morning. Yet when the engines worked as designed, they delivered a mechanical experience unlike anything else in the American military arsenal. The sound of a PT boat at speed was not the deep, rhythmic thumping of a diesel locomotive or a commercial tugboat. It was a high-pitched, synchronized mechanical howl. The gear-driven superchargers whined over the raw, unsilenced exhaust roar of 36 cylinders firing in rapid succession, a sound that could be heard for miles across the water. The Packard 4M2500 V12 had proven it could deliver the raw power the Navy demanded. It turned American torpedo boats into the fastest, most heavily armed small surface combatants in the world. But it also locked the military into a terrifying dependency. The engine was a mechanical triumph of American manufacturing, but trusting it in combat meant relying on a fragile ecosystem of mechanics, replacement parts, and the most dangerous fuel on Earth. By 1943, the Packard 4M2500 V12 was no longer just a prototype. It was the undisputed king of American gasoline marine power. Inside the sprawling Packard manufacturing complex in Detroit, Michigan, the assembly lines had achieved a relentless, synchronized rhythm. Thousands of massive aluminum blocks were being cast, machined, and assembled by a workforce operating around the clock. The engine that had started as a desperate laboratory experiment was now being shipped by the trainload to boatyards on the East Coast in the Gulf of Mexico. When Elko in Bayonne, New Jersey, and Higgins Industries in New Orleans, Louisiana, dropped these engines into their 80-foot plywood hulls, they were creating the fastest, heavily armed small ships in the world. The American military had successfully placed a 4,500 horsepower aviation powerhouse on the surface of the ocean. But the true scale of the Packard V12 empire was not measured in Detroit foundries. It was measured in the remote, punishing environments of the South Pacific, in places like Tulagi, Rendova, and the humid, mosquito-choked inlets of New Guinea. Here, the United States Navy had to build an entire service network from scratch. A service network, the dealers, mechanics, parts suppliers, and manuals that keep a machine running after purchase, is usually built over decades on dry land. The military had to build this one in a matter of months on islands that often lacked electricity, paved roads, or proper machine shops. The mechanics assigned to motor torpedo boat squadrons were not working in clean, brightly lit garages. They were working in the stifling, 100-degree belly of a wooden boat floating on saltwater. They were young men from Midwestern farms, California hot rod shops, and East Coast rail yards who had to suddenly memorize the complex tolerances of a supercharged, four-valve per-cylinder aviation engine. Every day they wrestled with massive Holley carburetors, synchronized complex linkages, and fought a never-ending battle against saltwater corrosion. The high-strung engines hated being idled during stealthy night patrols, which caused the carburetors to load up with fuel and foul the ignition systems. A mechanic's morning often began with the grueling manual labor of pulling, cleaning, and regapping 36 spark plugs before the tropical sun was fully in the sky. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat left the dock, a generator carried a hospital through a storm, or a plane lifted from the runway, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. For the crews of the PT boats, trust was a complicated equation. The Packard V12 gave them the speed to strike enemy destroyers and outrun the return fire. But that speed required living on top of a floating bomb. To feed the three supercharged V12s, the boats carried up to 3,000 gallons of 100-octane aviation gasoline. The fuel was so volatile that a stray spark from a dropped wrench, a shorted wire, or a single enemy tracer round could vaporize the boat in an instant. The engine room was a terrifying place. At wide-open throttle, the noise was beyond deafening. The gear-driven superchargers screamed, the 36 cylinders hammered, and the heat radiating from the massive exhaust manifolds pushed the temperature well over 120 degrees. The mechanics who monitored the engines during combat patrols stood inches away from spinning shafts and red-hot metal, knowing that beneath the wooden floorboards lay enough aviation fuel to level a city block. Despite the extreme danger, the demand for more speed never stopped. The early 4ME 2500 engines, known as the W14 series, produced 1,200 horsepower. But as the Navy bolted more armor, heavier guns, and radar equipment onto the mahogany hulls, the boats became sluggish. The boat builders and fleet commanders demanded more power to compensate for the added weight. Packard engineers in Detroit responded by redesigning the intake manifolds, altering the ignition timing, and increasing the supercharger pressure. This led to the W17 version of the engine, a mechanical marvel that pushed the output to a staggering 1,500 horsepower per block. A single wooden boat now possessed 4,500 horsepower. The speed returned, but pushing an aluminum block to those extremes came with a heavy cost. By 1944, the Packard Motor Car Company had built more than 12,000 of these massive Marine V12s. They were shipped out of Detroit by the trainload and installed into hundreds of Elko, Higgins, and Huckins torpedo boats. In the dark, unforgiving waters of the Pacific and the Mediterranean, the Packard 4M 2500 was no longer just a mechanical experiment. It was the defining sound of the American Mosquito fleet. But extracting 1,500 horsepower from a 2,500 cubic inch aluminum block had pushed the metal to its absolute physical limit. The W17 engines were running at such extreme internal pressures that the lifespan of the engine plunged drastically. In a traditional heavy marine diesel engine, the kind of engine that powered a commercial tugboat or a coastal freighter, an overhaul might not be required for tens of thousands of hours. An overhaul is a massive service process where an engine is entirely removed, taken apart, inspected, and rebuilt to factory operating standards. For the Packard V12, the Navy mandated a complete overhaul after just several hundred hours of operation. Under the brutal reality of combat, mechanics often had to pull the engines apart after less than 100 hours of wide-open running. The massive centrifugal supercharger forced so much pressure into the cylinders that the heavy steel connecting rods, the parts that link the pistons to the crankshaft, would physically stretch. The lightweight aluminum blocks would warp from the intense, violent heat cycles of running flat out at 40 knots and then suddenly idling in cold ocean water. This extreme wear created a staggering logistical burden. To keep the PT boats running, the United States Navy had to establish massive, floating machine shops and sprawling island repair bases. They had to ship tens of thousands of replacement carburetors, head gaskets, spark plugs, and entire spare engine blocks across the Pacific Ocean. The mechanics worked under canvas tents or open skies, using chain hoists to rip 3,000-pound engines out of wooden hulls. They constantly swapped fresh blocks into the boats while rebuilding the exhausted engines in the dirt. It was a brutal, relentless industrial rhythm that temporarily turned remote tropical beaches into greasy, oil-stained extensions of the Detroit factory floor. Yet the Navy accepted this immense maintenance cost because the Packard 4M2500 delivered exactly what it promised. It gave American sailors the ability to strike larger, heavily armored warships and disappear before the enemy could zero their guns. The high-pitched, synchronized scream of three supercharged V12s spooling up became a terrifying warning in the dark. The engine had proven that American manufacturing could take an aircraft design, force it into the ocean, and make it survive through sheer mechanical force and an endless supply of replacement parts. At its absolute peak, the Packard Marine V12 was the ultimate expression of wartime gasoline power. It was a machine that solved an impossible physics problem by simply burning an apocalyptic amount of 100-octane aviation fuel. It was an engine that demanded constant attention, punishing labor, and total fearlessness from the men who stood in its engine room. The Packard V12 had proven it could dominate the surface of the ocean, but the forces that would destroy it were not enemy ships. They were peace, economics, and a fundamental shift in how America understood fuel. The first crack in the Packard Marine Empire was not a mechanical failure in the South Pacific. It was a radio broadcast in the late summer of 1945 announcing the end of the Second World War. Almost overnight, the United States Navy canceled its massive defense contracts. The military no longer needed a fleet of wooden torpedo boats, and they certainly no longer needed the 4,500 horsepower engine rooms that made them move. The relentless rhythm of the Detroit assembly lines, which had churned out more than 12,000 of these massive supercharged V12s, ground to an abrupt and permanent halt. But the true decline of the Packard 4M2500 was driven by a fundamental shift in American naval doctrine. The military had tolerated the terrifying risks of the gasoline engine because wartime survival demanded blistering, immediate speed. But in peacetime, the equation changed. The Navy was forced to confront Force 4, fuel, oil, supply chains, and energy shocks. To keep a fleet of PT boats active meant maintaining a massive, highly specialized supply chain of 100-octane aviation gasoline. This fuel was incredibly expensive, highly volatile, and fundamentally unsafe for marine environments. Without the immediate threat of enemy destroyers, no naval commander wanted to order young sailors to sleep on top of 3,000 gallons of explosive aircraft fuel. The American military made a permanent pivot. For heavy, sustained naval work, the future belonged exclusively to the marine diesel engine, a machine that burned heavy, stable fuel that would not vaporize and ignite from a stray spark. And for the next generation of high-speed coastal vessels, the horizon was already shifting toward the gas turbine engine, an engine that uses spinning turbine stages and high-speed gas flow to produce continuous power, offering massive thrust without the violent internal vibration and catastrophic fuel risks of a supercharged piston block. The era of the high-horsepower gasoline marine engine was effectively dead. With the factory lines halted, the Packard Motor Car Company turned its attention back to building civilian luxury automobiles, attempting to survive the brutal post-war automotive market. But the thousands of 4M 2500 engines that had already been built did not simply vanish. The military faced a massive logistical problem. What to do with a sprawling Mosquito fleet that was now entirely obsolete? The Navy's solution was swift and brutal. Across the Pacific, hundreds of PT boats were stripped of their weapons and hardware, dragged onto beaches, and deliberately burned to the waterline. The military determined it was cheaper to destroy the wooden hulls than to ship them back to the United States. But the engines were different. A 3,000-pound block of precision-machined aluminum, packed with heavy steel crankshafts and advanced centrifugal superchargers, still held enormous scrap value. Thousands of Packard V12s were ripped out of the engine rooms, crated up, and shipped back to American shores, where they were dumped into military surplus yards from California to the industrial Midwest. This created one of the most bizarre market anomalies in American engine history. An engine that had cost the federal government tens of thousands of dollars to develop and build, a pinnacle of wartime engineering, was suddenly sitting in a dusty surplus lot, coated in cosmoline grease, bearing a price tag of $50 or $100. The engine was entirely useless for normal civilian life. A standard commercial fisherman could not afford to burn 300 gallons of aviation fuel an hour. A coastal tugboat operator needed low-end diesel torque, not a screaming high RPM supercharger. The engine was too massive to fit into a passenger car, too heavy for civilian aircraft, and too dangerous for standard pleasure boating. But it was exactly what a specific breed of American mechanics, hot rodders, and farmers had been waiting for. The Packard V12 was about to enter Force 8, the industrial afterlife. It was about to transition from hunting warships in the dark to terrifying crowds in the American Midwest. In the late 1940s and early 1950s, a new, uniquely American motorsport was taking shape in rural farming communities: tractor pulling. Farmers would gather to see whose modified agricultural equipment could drag a heavy-weighted sled the furthest distance across a dirt track. Initially, they used standard, low-compression farm engines. But when young mechanics like Art Arfons from Ohio wandered into a military surplus yard and saw a pristine Packard 4M 2500 V12 sitting in a crate for pennies, the rules of mechanical power fundamentally changed. Arfons and his brother bought the 2,500 cubic inch aviation monster, dragged it back to their shop, and bolted it to a crude steel tractor frame. They painted it green and called it the Green Monster. When that engine fired up on a dirt track in Ohio, running on open exhaust headers and screaming through its aircraft supercharger, it literally shook the ground. It was no longer a marine engine. It was a blunt force instrument of civilian horsepower. At the exact same time, on the lakes of Washington State and the rivers of the Midwest, civilian boat racers realized the surplus Packard V12 was the ultimate weapon for unlimited hydroplane racing. A hydroplane, a specialized racing boat designed to ride on a cushion of air and just a few inches of water, required terrifying amounts of power to achieve flight-like speeds. Mechanics began dropping the massive 2,500 horsepower Packard engines into wooden hulls that weighed a fraction of a fully loaded PT boat. On the water, the hydroplanes roared across American lakes at speeds exceeding 160 miles per hour, throwing massive rooster tails of water into the air. The engine had found a second life in the hands of American thrill seekers, but relying on a discontinued orphaned engine line built for a war that was already over was a dangerous game, and the surplus iron could only last for so long. The civilian afterlife of the Packard 4M 2500 V12 was thrilling, but it was fundamentally a trap. The farmers and hydroplane racers who bought these massive power plants out of military surplus yards were living on borrowed time. They had acquired world-class engineering for pennies, but they had also inherited an engine that was completely cut off from its original supply chain. When a tractor puller pushed a surplus Packard V12 too hard on a dirt track in Ohio, and a piston shattered under the extreme pressure of the supercharger, he could not simply drive to a local dealership to order a replacement. The tooling, The highly specialized molds, jigs, and heavy machinery required to manufacture a specific engine block or component was no longer producing marine engines. Packard had completely shut down the 4M 2500 production lines in Detroit. The only way to fix a broken surplus engine was to cannibalize another surplus engine. By the late 1950s, the racing world began to abandon the Packard. In the unlimited hydroplane racing circuits, mechanics realized that while the Packard was a phenomenal marine engine, it was incredibly heavy. It weighed nearly 3,000 pounds because it had been reinforced with heavy reverse gearing and marine cooling systems to push an 80-foot wooden military boat. Racers quickly discovered they could go faster by buying surplus Allison V1710 aircraft engines. The Allisons were pure aviation blocks, hundreds of pounds lighter, and because they had been built in vastly larger numbers for fighter planes, their replacement parts were much easier to find. As the crate engines dried up, the massive Packards were slowly pushed out of American garages and boat sheds, left to rust behind workshops as their internal components became impossible to source. But the final blow to the Packard 4M 2500 was not delivered by a lack of spare parts on the racing circuit. It was delivered by the catastrophic collapse of the Packard Motor Car Company itself. The company that had solved the Navy's most desperate power problem during the Second World War could not survive the brutal economic realities of the peacetime American automotive market. Throughout the 1950s, Packard found itself completely outgunned by the massive manufacturing scale of General Motors, Ford, and Chrysler. In a desperate bid to survive, Packard merged with the Studebaker Corporation in 1954, forming the Studebaker-Packard Corporation. It was an alliance of two dying empires, and it did not save either of them. By 1956, the legendary Packard assembly plant on East Grand Boulevard in Detroit, the exact same sprawling industrial complex where thousands of workers had once cast, machined, and assembled the mighty 4M 2500 Marine V12s, was permanently shuttered. The foundries went cold. The machining lines were dismantled. The corporate memory of how to build a 2,500 cubic inch aluminum sea monster vanished into the wind. 2 years later, the Packard nameplate was effectively dead. The brand that had defined American luxury and wartime naval dominance was reduced to a discontinued badge. Even if Packard had survived, the engine would not have. The United States Navy, the only customer that ever truly needed a 1,500 horsepower gasoline marine engine, had completely rewritten the rules of high-speed naval warfare. The military had fully embraced Force 5, convenience and technological displacement. For heavy coastal patrols and fast attack craft, the Navy shifted to advanced marine diesel engines. A modern turbocharged marine diesel could produce massive torque, offer vastly superior fuel economy, and, most importantly, burn a stable, heavy oil that would not instantly vaporize and explode if a fuel line ruptured in a firefight. For ultimate high-speed surface vessels, the Navy bypassed piston engines entirely and adopted the gas turbine. A gas turbine engine, a power plant that uses continuous combustion to spin turbine blades, producing massive shaft power or thrust, changed the geometry of naval architecture. A turbine did not have 36 massive pistons violently hammering up and down. It had a smooth, continuous, rotational hum. It produced thousands of horsepower while weighing a fraction of a comparable piston engine, and it ran on standard military jet fuel rather than highly volatile 100-octane aviation gasoline. The Packard V12 had been engineered for a highly specific, terrifying window of American history. It was the absolute pinnacle of what could be achieved by forcing a spark-ignited aircraft engine to survive in the ocean. But it was a technological dead end. It relied on a fuel that was too dangerous to carry, a service network that was too expensive to maintain, and a company that no longer existed. By the 1960s, the wooden PT boats were ashes on Pacific beaches, the surplus crates were empty, and the Detroit factory was an abandoned shell. The engine that had once terrorized enemy fleets was reduced to a heavy, silent block of aluminum sinking into the weeds behind rural American machine shops. The engine still ran. The surplus dried up. The racing teams moved on. The factory lines were dismantled. The military rulebook changed. The aviation fuel became too dangerous to carry. The high-pitched supercharger sound faded. The wooden boats were burned. The badge remained. The world it powered was gone. The Packard Motor Car Company did not survive to see its wartime engineering become museum pieces. The sprawling manufacturing complex on East Grand Boulevard in Detroit, Michigan, the exact place where thousands of American workers once cast, machined, and assembled the mighty 4M 2500 Marine engines, eventually became one of the most infamous industrial ruins in the United States. The company that defined American luxury automobiles and solved the United States Navy's most desperate maritime power problem collapsed under the weight of post-war corporate consolidation. By the time the 1960s arrived, the Packard badge was dead, and the factory floors that once vibrated with the testing of massive V12 blocks were silent and abandoned. But the Packard 4M 2500 did not entirely vanish from the American landscape. Today, its survival rests in the hands of an incredibly small, fiercely dedicated community of historical preservationists, mechanics, and maritime museum volunteers who refuse to let the sound of a supercharged Marine V12 die. In Portland, Oregon, a group of aging mechanics and naval historians maintain PT 658, one of the only fully operational motor torpedo boats left in the world. Down in the cramped, humid engine room of that preserved wooden hull sit three original, functioning Packard V12s. To keep these massive engines running today is an act of grueling mechanical archaeology. There is no dealership parts counter. There is no modern supply chain. When a head gasket blows, or a piece of a massive Holley downdraft carburetor fails, the mechanics cannot simply order a replacement. Instead, they must rely on decaying, oil-stained military service manuals from 1944. They have to machine their own custom replacement parts on traditional lathes. They scour farm auctions, estate sales, and remote marine salvage yards hoping to find a cracked surplus block that can be cannibalized for its heavy steel connecting rods or original spark plug wires. They trade rumors on internet collector forums about forgotten crates of surplus engine parts rusting away in Midwestern barns. Every time they fire up the engines, they are managing a fragile, irreplaceable piece of industrial history that requires constant tuning, extreme patience, and a deep understanding of a mechanical language that most of the modern world has forgotten. This is not nostalgia. A surviving Packard 4M 2500 V12 sitting under the museum lights or rumbling inside a preserved wooden hull is a physical argument about a vanished era of American manufacturing. It is a reminder of a time when the solution to a massive physics problem was pure, unrestrained mechanical force. It proves that there was an era when American industry responded to a crisis not with software, microchips, or complex digital management systems, but by casting an aluminum engine block the size of a dining table, strapping a gear-driven supercharger to it, and feeding it the most explosive aviation fuel available. It represents a world where power was deeply, physically connected to human labor. The engine did not run itself. It required a young mechanic standing in a 120-degree engine room, perfectly synchronizing three massive throttles by ear, feeling the vibration of 36 cylinders through the floorboards. As a strange footnote to its legacy, the Packard Marine engine actually helped plant the seeds for America's post-war horsepower obsession. When thousands of young mechanics returned home from the Pacific Theater, they brought back the mechanical knowledge they had learned in the engine rooms of the Mosquito fleet. They had spent years tuning 1,500 horsepower supercharged engines. When they returned to American garages and began building hot rods, dragsters, and hydroplanes, they carried with them a profound appetite for massive displacement and forced induction. The engine had taught an entire generation of American men that there was no physical limit to how much power you could make if you were willing to burn enough fuel. But America did not stop needing power on the water. It simply stopped needing that kind of power. The military, the commercial maritime industry, and the civilian boating market all shifted toward the steady, reliable torque of the marine diesel engine, or the smooth, lightweight thrust of the gas turbine. Efficiency, safety, and fuel economy replaced raw, gasoline-fueled aggression. The era of strapping an aircraft engine into a wooden boat and hoping it didn't explode was permanently closed. Yet for those who know where to look, the ghost of Detroit's greatest sea monster is still out there. Somewhere in a deep-water harbor, an 80-foot mahogany boat pulls away from the dock. Down in the cramped engine room, A mechanic adjusts a massive carburetor, the smell of rich aviation gasoline filling the humid air. The throttles are pushed forward, and suddenly the water is violently disrupted by the high-pitched, synchronized scream of three supercharged V12s, a towering, deafening wall of sound that proves for just a few minutes that the ultimate American gasoline engine still refuses to go quiet. See you in the next one.